here's a couple memes kind of sprinkled out here and there, so hope you enjoy them. Okay, so the kind of a new topic that's a bit different to methods is these inverse and reciprocal circular functions. So you will have seen some reciprocal functions in methods, but you most likely haven't seen inverse circular functions before this time. So there are these two new families, and they're really good to have in the reference book to just kind of keep it and like to have the different ones and how they look and how they can be translated in the reference book. I would say for reciprocal functions, they're probably, the graphing of them is quite similar just to graphing the normal function and then essentially just flip it. For graphing the inverse circular functions, we'll talk about a system to kind of graph them and work through them, but I find them easier to graph than just the ordinary circular functions because they're a lot more structured and there's kind of less things that can go on with them. So try to memorize the shape of the graph, or I would say more than memorize, just kind of be familiar with the shape of the graph and know approximately what it looks like. A lot of them you can kind of, because they are kind of manipulating the circular functions we have in the first place, there's a lot of things that we can do just to kind of change. We can kind of, from first principles, logic what they look like, but obviously it is easier if you know the general shape of the functions and know what they generally look like, because that way you know what to expect when you're kind of doing these types of things, and also it might just be a more efficient process for you overall. But I would say that just try and be familiar so you know approximately what types of graph it looks like. If you really can't memorize it, you can always kind of build it up from first principles. So a reciprocal function, just applying reciprocal function things to circular functions, and applying like inverse function things to the inverse circular functions. So a couple things that you need to know is the domains, the ranges, and the transformations, how to sketch them, and how to solve equations and inequalities involving them. Righty. And you will have to do calculus with them as well. I would say that calculus you'll get like, in your bound notes, you'll get a whole set of kind of equations to do the calculus for the inverse circular functions. You won't really have formulas for the reciprocal functions besides sec because of its relationship with tan, but you should be able to first principle logic it using the chain rule along with the differentiation rules you already know. Alright, cool. Let's talk about reciprocal first. So what we do is we just put the trig in the denominator. So cosec is, let me get a pen up. So cosec is going to just be 1 over sine. So cosec is going to just be 1 over sine, which is what we have here. And we'll have like cos equaling to sec and tan equaling to cot. So the most important thing here is that we recognize what each of these things are. So the easiest way to memorize this is cot is kind of unique by itself because just like tan and cot, they're like the odd black sheep of the family. They're that odd one that's kind of left out. So it's like if you had twins and then like, I don't know, another brother or sister, it's similar, but it's always not going to be the exact same, right? So for sine and cos, because there is a really intimate relationship between the two, I kind of focus on trying to not confuse those two together. So the letters swap, so sine goes to cosec and cos goes to sec, and then tan goes to cot. Okay. I guess you can kind of remember the tan goes to cot as both of them include t's, right? And it's the only ones that include t's and not all of them. Alright, so how to draw these without memorizing? We have to draw the base trig function, and then we draw the vertical asymptotes at the x-intercepts, and then we can so we draw the base trig, so let's just kind of go through that together. So let's say if we're just drawing the base sine function, and then we draw asymptotes at the intercepts because 1 over 0 is undefined. So we'll have an asymptote there, and asymptote here. And then remember, for reciprocal functions, max becomes mins and mins become max. So we'll have a minimum here and a maximum here. And importantly, if there's no vertical translation on the thing, there's also going to be an asymptote kind of y equals to 0 as well, because we'll never be able to get a 0 point in terms of we'll never be able to reach those 0 points that we reach by the x-intercepts. Therefore, we'll also never be able to reach 0 on the axis here as well. So that's what you kind of see there. And then that's kind of the graph we get, and you just repeat it for how many periods you want. Evidently, it's a bit more funky once we get talking about, actual transformations and stuff. But the easiest thing to do is essentially just do this. Reverse the function that they've given you, and just do this until you reach to a point. And then, because it might give you something like cosec 2x plus 3 plus 5, right? So, or like 2 cosec blah blah. So what I would do is I would focus on I would get away from I would get rid of the plus 5 for now, and I'd focus on this segment and find what a half, that says should equal to cosec rather than cosec. I said cosec, but I wrote cos. So cosec, so that's going to just be a half sine 2x plus 3, right? And then what we're going to do is we find out how to graph that one first. And then once we do that, all we have to do is just put the plus 5 at the end for what that is, and we can find the new x-intercepts, draw in the new asymptote, etc. But the actual coordinates of all the vertical asymptotes will be the same, and the turning point, x position should be the same, but everything's just going to be shifted 5 upwards. And I find that's the easiest thing to do, especially when you have a lot of transformations going on. For tan, so the tan function is like this. So the cot function is literally just the reverse of that. So it has the asymptote here instead of here, and these become x-intercepts. So essentially, when we have this, we'll have this instead, and it'll just go down like that. So it'll come that's an asymptote. So it'll come like that, and then we'll just have, we'll have this bottom half of the function there. Sure, a little bit too forwards. Oopsies. Okay, so we'll have this bottom half of the function here, kind of coming into here, and then we'll have the top part coming up there. So everything that was an asymptote before now becomes an x-intercept. Everything that was an x-intercept becomes an asymptote. And a cot graph is pretty easy to draw just by itself, because it's essentially just a reflected tan graph. Or you could even say it's like a reflected and then translated tan graph, essentially. Okie dokie. Alright, so let's chat about each of these functions a little bit more in detail. So cosec nx is 1 over sine nx, like we talked about before the letters swap. So importantly, the domain is no longer just R, right? Because now we have asymptotes there. And if we think of where the asymptotes would be located, they're going to be located when sine nx equals to 0, right? And we know that sine nx, so sine in terms of when it equals to 0 is here and here, right? So 0, pi, 2 pi, 3 pi. So therefore we're going to think that it's going to be basically pi n, or pi k, let's say. So it can be any number of cycle of the pi kind of numbers. So therefore we're just going to get x equals to pi k over n. And that's where we can kind of see what's going on. Alright. So then in terms of the period, it's going to have the same period. So that's the domain. That's why we have that asymptotes there. In terms of the range, it's just basically because of that's where the minimums and maximums are, and the smallest value versus the largest value, and that's why we have a range which is excluded there. But if there was manipulation, so if this was like 2 cosec nx instead, there would be differences in where it would be. Like this would be a half versus this being -1. So it kind of just depends on what the vertical, like what is the values here and here. As in, is there any vertical translations? Is there any dilations from the x-axis? So that will kind of determine which range of values cannot be taken. Essentially, all you need to look for here is where is the difference between the two turning points, and then you can just put that into there. The period is going to be kept the same because it's the same function except just 1 over the function, so the period is going to be unchanged. It doesn't change how much time it repeats over, and we already talked about the asymptotes. Cool. So sec is very, very, very similar. It's just 1 over cos nx. And remember, that's just basically because of the relationship that sine pi on 2 minus x will just equal to cos pi on 2. Cos x, right? So that's why it's just literally a shift in terms of where it's really going. So what we're going to do here is we can kind of see that now the asymptotes, now we're looking for when cos nx is going to be equivalent to 0, right? And we know cos, in terms of where it's negative, it's going to be, in terms of when it's 0, it's going to be here and here, right? Top and bottom. So it's going to be pi on 2, 3 pi on 2, 5 pi on 2. So it's going to be every negative pi on 2. And we, doing kind of the proofing topic and all that kind of stuff, we might be a little bit more comfortable with how we can phrase that now, because it's going to be every 2k, which is the even one, plus 1. And that's going to give us our odd one over 2n times pi. So that's going to give where our odd asymptotes are. And the n component is just because we have the n there. Cool. Once again, the range is just going to be everything excluding the space between the minimum and maximum kind of turning points, and that's going to tell us where it is. Alright, so then the period, once again, it's going to be unchanged because the putting 1 over something isn't going to change how often this graph repeats. And then we already talked about how the asymptotes work there. Okie. So with cot function, the cot function is essentially the exact same as the tan function, except it's been translated across backwards by pi on 2. So this point used to be here, and it's been reflected in the x-axis. So that's really the only two differences, but it just still looks like a tan function. So importantly, now we want to know when tan nx would have equaled to 0, and we know that's going to be at this position. So once again, it's going to be k pi, so we're going to have k pi equals to nx, and then x would equal to k pi over n, which gives us our asymptotes. The range, just like the range for tan is -infinity to infinity, the range for cot is also -infinity to infinity, because as it approaches the asymptotes, it's going to go to positive infinity and negative infinity. The period is unchanged once again. Sorry, that should be pi over n rather than pi n. So it's going to be unchanged compared to what it was before, because putting 1 over something isn't going to change how often the graph repeats. So we already talked about the asymptote, and you can kind of see how if we said pi on 2 minus x, that's going to be, so that's a translation of pi on 2 to the right, and then we reflected it in the x-axis. Reflected it in like the axis, right? Because we've just kind of made it positive to negative. Cool. Awesome. Alright, so these are the formulas that we need to talk about. So these formulas, most of the formulas should be in your formula sheet, but I think all of the formulas here should be on your formula sheet. They are really, really, really good. Like, they will come up so much through complex numbers, through calculus, through circular functions in itself. They come up so much, and they can be very useful in any type of like topic, essentially, because they can come up, like, cause circular functions can be integrated into any other of the topics that we're talking about. So it's really good and useful to kind of know what they are and how to use the formulas appropriately. So even though that they are on the formula sheet, it's good to have them at the back of the mind, especially for efficiency. And sometimes you'll have to do something called the half angle formula proof. So what you do instead is, so when we look at something like this, so we have, instead of doing like the half formula, so what you do instead, a really common example is like cos pi on 8. And essentially you just make cos 2 times pi on 8 equivalent to cos pi on 4, and then you kind of work backwards from there. Right. Inverse circular functions. These are good to kind of memorize the shape of the graph and like just kind of know the gist of the graph. You can always use first principles, but it's always useful to kind of know what they look like. And because they're inverses, they're going to be cut off at certain points because of the turning points involved in a circular function, so that we can have a one-to-one curve. So how we can kind of draw is, if you didn't want to memorize it, you could just draw the basic trig, try to reflect it across the line, and then take the maximal domain to be one-to-one, and then kind of restrict and do whatever you need to do from there. Another thing is that if the inverse is on the inside, we can kind of cancel it across. If the inverse is on the outside, then we can't cancel it across. It's not always equivalent. And that's essentially just because if you think of something like, let's just use sine. So sine inverse of sine, actually let's talk about on the next slide because it would make more sense once we can see the domains and ranges of these functions. Alright, so for this one, right, the domain is negative 1 to 1. That's just basically because the base sine function, remember, it can only go from, the amplitude is at max negative 1 to 1, and that's because of the properties of the unit circle. That's the maximum values that sine and cos can really take, because of the unit circle only goes 1 to negative 1, right? So that's why it's the domain, and because it's the inverse, this was the range before, but now it's flipped into the domain. Okay, so in terms of the range, this is literally just arbitrary. Like, they've just picked a point which is a little bit arbitrary, and to be very honest, like, it doesn't really have any real particular reasoning why they chose this range over like a period before that or a period after that. Like, there's not really an implication per se of what they're trying to do here, unfortunately. So they've just tried to exclude any turning points, but there's no reason that it couldn't have been pi on 2 to 3 pi on 2. Like, there's not really a reasoning for that. It's just what they chose. But what we just need to remember is it's negative pi on 2 to pi on 2. Okay. So let's go back to that thing of sine inverse sine x does not always equal to x. So if we imagine sine inverse sine of, let's say, 2 pi and 3, right? Okay, so this cannot be equivalent to 2 pi and 3 because that's outside of the domain, outside of the range for sine, right? Like, that's not possible. It's outside of the range for sine inverse. So what we have to do instead is, when we look at this, what happens is we have sine inverse, and then we'll have something like, so 2 pi on 3, that's in the positive quadrant of sine, and pi on 3 of sine is just going to be root 3 on 2. So then we can kind of convert it backwards to what equivalent would be in this domain, in this range, and that would mean that the equivalent here is going to just be pi on 3, right? Because in pi on 3, when we sub it into there, it's going to be equivalent. So yeah, so we just need to keep that in mind in what we're trying to do. Okay, alright, so for cos, the domain is the same thing, because once again, you can only go from negative 1 to 1, and that's kind of the maximum values you can really take for the base cos function. But then in terms of its range, once again, it's a little bit arbitrary, so they just took 0 to pi, so 0 to pi, and it's very arbitrary in what they actually took in terms of the values. So my honest opinion is they just took negative 1 to 1 and picked one of the sets of values that it could be. So there is no reason why they didn't pick, let's say, for example, they could have also done pi to, they could have also done, yeah, they could have done pi to, let's say, 2 pi as well, or they could have done negative pi to 0 as well. Like, doesn't actually matter too much, because regardless of what you're doing, negative pi, they're always going to give you the same values of what you're trying to do here. So this could have, if we drew like another version of this graph along, this could have been from, if this was pi to 2 pi instead. So our domain here would have been -1, right? So that would have been -1 pi, -1 pi, right? Because when we sub in -1, we're going to get pi. And then if our range was there, it would have just been a translation. Sorry. Would have been a translation up to the 2 pi, right? Because when we sub in 1 into there, it would have just given us pi instead. Would have given us 2 pi instead. So there's not a particular reason, unfortunately. It is just what convention what values they chose to really stop it off at. Because if you imagine our graph of 0 to pi, it's going to look something like this. So 0 to pi, like that, right? There's no reason that they couldn't have taken it this side, or they couldn't have taken this side, except that I guess if you look back at the two graphs, you would be elevating it above the axis or putting it below the axis. So you could be technically you would be able to get something like this instead, right? That would be your graph instead. But in the large scheme of things, it doesn't actually matter too much. They just picked a thing and went with it. Okay, cool. So the tan function is arctan, and it just looks like a cube root function, to be very honest, but it's just a tan function on its side. So because the asymptotes were this way before, now the asymptotes are horizontal. So because the asymptotes are horizontal, that means we just cut off the edges of the range that we're working with. And once again, because if we went across that way, if we think about a tan function normally and it goes like this, like that, if we cut across there, we can see that more than one value is possible. So they just chose one of them to use, and that was the negative pi on 2 to pi on 2, 1. So that's really just what they did. And the domain here is R, so remember the domains and ranges flip. So the domain before was R, the range before would have been R, and now the domain is R, and before the domain would have been excluding every odd pi on 2 type thing, but now because we're only using one thing, we can just write it as negative pi on 2 to pi on 2. Cool, awesome. All right, let's chat a bit about how we evaluate these. So the first one, what we're actually trying to ask is what angle will give you a half when we put it into sine. And if we use our wonderful triangle here, we're going to be using the 2, 1, root 3 triangle, and we're looking for a half. So sine is opposite over hypotenuse, so therefore we're going to be looking for pi on 6. So this is going to just be equivalent to pi on 6. Cool. Alright, so cos inverse of cos negative pi on 3, right? So what we have here is that situation from before. So if we think of where cos pi on 3 is, negative pi on 3, it's here, right? So cos negative pi on 3 is going to give you just going to give you positive a half in terms of the value of it. And what that means in our terms is now we have to think what value of cos inverse will give us a half. And remember, our domain for cos was 0 to pi. So therefore, if we want a positive one, we would just be thinking that's just going to be normal pi on 3. So the thing we have to be really careful about is that it fits within our domain, because we can kind of do a quick check. If it was to fit within our domain of, if this was just pi on 3 or 2 pi on 3, it fits within our range of our function. So therefore we can just accept it straight away, but because it doesn't, we can't really accept it. Cool. Okay, so this one has the normal function and the inverse on in the inside, but the only problem is it's not the same function. So not the same function. So therefore we can't do the thing from before where we just directly rule it out. Instead we have to kind of go into a little bit more detail. So the thing with this is we think to ourselves, okay, negative pi on 4 sine inverse. Yeah, that's just root 2 on 2. Nope. It's actually, because it's the inverse of it, it's not asking for the sine of negative pi on 4. It's asking for the sine inverse of negative pi on 4. And remember, sine equal to opposite over hypotenuse. So what we can actually pop down is that this is going to be the equivalent of saying that this part is going to be 4, and this part, let's just say it's that angle there, this part is pi. So therefore, using Pythag, you'll get that this is 16 minus pi squared in terms of the last side there. Alright, so then we have to decide whether this is positive or negative, right? Because if it's positive or negative, we'll kind of determine which side it is. So if we consider sine of inverse pi, like negative pi on 4, sine is only negative when it's in this or this quadrant, right? That's a thing for us. It's only ever negative when it's in the third or the fourth quadrant. And that would mean that this angle, the result of this would have to either be in the third or fourth quadrant. Now, then we have to say to ourselves, okay, is it going to be in the third or fourth quadrant? And in fact, your calculator will do the same thing. If you pop it into your calculator and try to put in the answer of like what this is actually equivalent to, it will try and do the same thing as you've been doing kind of up here as well. So we have to decide whether it's the positive or the negative version of 16 pi on 2 minus, not pi on 2, pi squared over 4, right? Okay, so we kind of need to know a little bit more details about this as well. So we know that the sine inverse, the output of sine inverse, right, can be from -1 to 1. So what that means for us is, in terms of the values, it can be in here or in here. So it can be -1 or 1. So it can be either here or here, right? Because we're trying to sub it in for the angle. So it can be in like this part or this part. So we kind of get that it's going to be here or here, right? Which doesn't really help us conclude where we're really going. But essentially, when we look at this and we can see that this angle is going to be a negative pi on 4 rather than a positive pi on 4, we get that this value is going to be a negative. And then when we sub in the negative value into whatever this is, right? And because also, you know that sine of, so pi on 4 is approximately about 3.14 ... right? So therefore we know that it's not going to really reach it's not going to reach this, like when we have that over 4, right? It's going to be 3.14 over 4 ... right? So we're going to get that this is going to be 0.9 something overall. So what that means is, because pi on 2 is about 1.7, we know that it has to be in this quadrant instead, because it's about 1.7 something. So if it was in this quadrant, it should be bigger than 1.7 in terms of when it's a negative value. So therefore we can kind of conclude from that we just have root 16 minus pi squared over 4, as we have that this number is actually smaller than pi on 2. Right, because that's really the only conclusion we need to find. Is that this number bigger than pi on 2 or smaller than pi on 2? Cool. Awesome. Alright. So then what we can look into is the domains and range. So this is a really nice table to kind of work with, and I think it's a really good one to kind of utilize and have handy. So with domains for our inverse circular functions, what we want to do is undo the transformations, because we must have everything fit between the -1 to 1, right? So we make whatever's on the inside equivalent to that, and then we kind of undo all the things. With ranges, we have a base thing of it's between -pi on 2 to pi on 2, or it's between 0 to pi, And then from there, we kind of can expand out because things and stuff are being added to them slash timesing them to make it bigger and bigger. So let's have a look for this question. So let's say we have A sine inverse B x minus C plus D. Okay, so for the domain, we undo. So we take the bracket out. So we take this part of the bracket and then we apply the negative 1 to 1. So we get just bx minus c, and then we need to figure out what x values it can take for that to be able to be happen. So we put the c across and then divide by b, which gives us, it'll be c minus 1 over b to c plus 1 over b. Alright, so then for the ranges, what we do is build up. So we have the base range, right? And we say that y minus d over a is equivalent to the base range. And then we can kind of build it up by there. So we times everything by a and then add the d across to kind of get the overall range of the function. And this works the same way for cos as well. And for tan, so this works the same way for cos inverse as well. For tan inverse, I guess the only thing is that the range would work in the same way, that we kind of can build it up, but the domain you don't need to really investigate that much because it's already R. So regardless of what we really do to it, it won't really change it too much. Cool. Alright. So solving equations, it's essentially just everything the same, except we just need to make sure that we have, like, we're just integrating reciprocal and inverse functions now. So the thing is that you need to make sure you have it in the correct domains and ranges, specifically, especially for when we're talking about like the inverse functions, because they have a very specific range and domain. So make sure you use a lot of compound angles, make sure you use a lot of double angles, and then for these types of questions, we kind of did that type of questions, but just use like triangles to help you visualize what's going on. Cool. Alright, so let's go through solving this question together. So it's sec 2x equals to cosec 4x. Alright, so the first thing that we can kind of identify from here is sec, remember that's going to just be 1 over cos 2x, and this is going to just be 1 over sine 4x, right? Okay, because they're both 1 over, we can just flip both of the fractions and to give us the same thing. So now we'll have this as cos 2x minus sine 4x, right? Okay, cool. So then from there, we can kind of solve from there. And a really important thing for just circular functions and maths in general is that you don't just like reject a solution and kind of expel it into Narnia. You must actually keep all of your solutions and just minus things across until, so it's kind of just like if you had x minus 2 equals to 0, you wouldn't suddenly just be like, okay, x equals to 2 equals to 0. You would still keep the stuff from before as well. You would say x equals 0 or x minus 2 equals to 0. Okay, so we need the same base in order to solve for these. So we're going to change this one using the double angle formula to change this one into this equation instead. So 2 sine 2x cos 2x instead of sine 4x. And then what we're going to do is group, just like if we had x squared minus 2x, and we could group it into x minus 2, we're going to group out to the cos here. So we'll get 2 sine 2x minus 1 and cos 2x. So what that means is sine 2x will equal to a half, because cos 2x cannot equal to 0, because otherwise this would be undefined, right? So we just state why we're not pursuing one of the paths further. So then we can so it's important to also like look at the restrictions in the domain and minimals and maximal domains and all that kind of stuff. So just keep that in mind as well. So then what we can do from here is kind of pursue that further, and we can now kind of look at actually finding solutions. So just kind of briefly to touch on finding solutions. So we look at our triangle, it's our 2, 1, root 3 triangle. Once again, we're looking for this angle up here, so it'll be pi on 6th. Then we check which quadrant it's in, so it's going to be in quadrant 1 or in quadrant 2, right? And our domain is 0 to pi, but we'll have 2x will therefore equal to pi on 6 or 5 pi on 6, right? So therefore we'll have x will equal to pi on 12 and 5 pi on 12, right? So from there we can kind of take it from there, that 5 pi on 12 and pi on 12. But if it wasn't in the domain, we can always add or minus domains to really get it in there. Right, cool. Right, so that is circular functions. Let's talk